Welcome to The Explainer. Today, we're diving deep into a massive shift in the world of computing. We're talking about NVIDIA's huge leap from its Hopper chip, the one that's dominated everything, to its brand new beast of an architecture, Blackwell. And trust me, this is way more than just a simple upgrade. It's a whole new way of thinking about how we power AI. So, let's get right into it.
So let's start with why this is even necessary. What's the problem they're trying to solve? Well, simply put, AI is getting too big, too fast. The complexity of these models is literally doubling every single year. And that means we're hitting a wall, a huge computational and energy wall that's pushing even our most powerful systems right to the edge.
Now, before we can really appreciate the new solution, we've got to give credit where it's due. We have to talk about the reigning champion, the Hopper architecture. For the past couple of years, this GPU has been the absolute workhorse behind this entire AI revolution we're living through, not to mention a powerhouse in traditional supercomputing. It really set an incredibly high bar. See, Hopper wasn't just about raw speed. It was incredibly smart. It brought in things like 4th-gen tensor cores, that's hardware built specifically for AI math, and this really clever transformer engine that could switch up the precision of its calculations on the fly. That, plus new data formats, made training these giant language models way faster than anyone thought possible. Hopper really was the engine of the AI boom. But, in this space, what's a breakthrough today becomes tomorrow's bottleneck.
And that's where Blackwell enters the picture. Look, it's so important to get this. This is not just an incremental update. NVIDIA's CEO, Jensen Huang, he called it a processor for the generative AI era. And he's right. It's a total redesign. You can think of it as a specialized AI factory built from the ground up to smash through that scaling problem we talked about. So, the biggest, most mind-blowing change is how Blackwell is actually built. Instead of trying to make one single gigantic chip, which is getting physically impossible, NVIDIA figured out how to fuse two absolutely massive GPU dies together. And they're connected with this wickedly fast 10 terabyte per second link, so they act like one enormous unified processor. It's a genius move that just blasts past the physical limits and memory walls that single chips run into, opening the door for truly colossal AI models.
The second game changer is the new transformer engine. It's even smarter about how it does math. It introduces this new super low precision format called 4-bit floating point, or FP4. Basically, think of it like using simpler, rougher numbers to get calculations done way faster, but without really losing any meaningful accuracy. The impact of this is just massive. It means training times could shrink from months down to just days, and it's going to use a whole lot less energy to do it. Okay, just take a second and look at these numbers, because they're absolutely wild. We're not just inching forward here. We're going from 80 billion transistors to 208 billion. The amount of memory more than doubled. The speed of that memory and the links between chips, again, more than doubled. This isn't evolution, people. This is a full-blown revolution in pretty much every spec you can measure. So what does all that new architecture actually get you? Well, it gets you this number, 20 petaflops. That is Blackwell's peak theoretical performance just for AI tasks, using that new FP4 math. To put that in perspective, that's a 5 times leap in raw AI compute power over the last generation. 5 times.
And this chart really tells the story perfectly. Even if we do an apples-to-apples comparison using the exact same FP8 data format that Hopper used, Blackwell still more than doubles the raw processing power for AI. And that is just absolutely essential for training the kind of massive, cutting-edge models that are pushing the industry forward.
Okay, but here's where it gets really interesting. There's a twist. This slide shows a critical trade-off. Some benchmarks are showing that for certain traditional scientific computing jobs, classic stuff like dense matrix math, the older Hopper GPU can actually be faster. This tells us something huge. Blackwell's insane specialization for AI has come at the cost of some of its performance as a do-everything general-purpose computer.
So, here's the bottom line. We are watching a great divergence in how these chips are designed. Hopper was built to be this powerful, all-purpose workhorse. It was fantastic at scientific computing and at AI. Blackwell, though, it's different. It's a hyper-specialized AI factory, and it's willing to trade some of that all-around skill for just jaw-dropping performance on generative AI.
Now, as you can probably guess, all of this incredible, record-breaking performance, it comes at a price. And I'm not just talking about the sticker price of the chip itself. I'm talking about the huge demands it's going to place on power grids and the very infrastructure of our data centers. And the difference in power and cooling is, well, it's pretty stark. A Hopper H100 GPU pulls around 700 watts. A lot of existing air-cooled data centers can handle that just fine. A Blackwell B200, on the other hand, is drawing somewhere between 1,000 and 1,200 watts. That's so much heat in such a tiny space that, just blowing air on it isn't going to cut it anymore.
So what does that mean? It means that adopting Blackwell isn't just about slotting new servers into your racks. Oh no, it means you have to fundamentally overhaul the data center itself. We're talking direct-to-chip liquid cooling on every single GPU, which then means you need massive, facility-wide chilled water pipes. That's a retrofit that can cost hundreds and hundreds of dollars for every square foot of your building. And then you add the cost of the GPU itself. The rumored price tag is over $50,000 for one. So you can see how this quickly becomes a massive, massive capital investment for both the chips and the building you need to house them.
So this all leads to the real question, right? It's not about which GPU is better. It's about which one is the right fit for you. If you're working with the kinds of models we have today and the data centers we have today, then Hopper is still the smart, pragmatic choice. But if you're building for the future, for 2026 and beyond, for those insane trillion-parameter models, well, Blackwell's power and efficiency are just in a totally different league.
And really, that's the main takeaway for most people right now. Hopper is not obsolete, not by a long shot. For today's workloads, it's still the best financial and practical choice. You can think of it as a really powerful, really necessary bridge to the new era of computing that Blackwell is about to kick off. But let's be crystal clear about where we're headed. NVIDIA is claiming that for inference, which is the part where you actually run the AI model, Blackwell is up to 25 times cheaper and more energy efficient. This isn't just about making AI more powerful. This is about making it truly sustainable on a global scale.
So this whole trend, this great divergence, it leaves us with a really fascinating question to chew on. As our most powerful hardware gets more and more specialized for just AI, are we accidentally moving away from the general-purpose machines that have fueled scientific discovery for the last 50 years? And what could that mean for the next great breakthrough? It's a heck of a thought to end our explainer on.